Welcome to The Calm Scientist. If you're here, it probably means you're ready to slow down, relax, and drift gently into the night with a head full of curiosity about the most mysterious and beautiful aspects of our universe. Tonight, we're going to unravel the strange, wonderful world of quantum mechanics, where particles dance between existence and possibility, where observation changes reality itself, and where the very notion of what we call real becomes delightfully, bewilderingly slippery. I do hope this won't be terribly inconvenient for your plans to fall asleep tonight, though something tells me quantum mechanics might just be mysterious enough to lull your mind into that perfect state of wonder and confusion that leads to the most restful dreams. After all, it's the kind of bedtime story only physics could write, complete with particles that exist in multiple places at once, cats that are simultaneously alive and dead, and a universe that seems to operate on rules so strange that even Einstein called them spooky. Before we dive into this quantum rabbit hole together, if you're enjoying this gentle journey into the heart of reality's greatest mystery, I'd be wonderfully grateful if you gave this video a like and subscribed. It truly helps this peaceful little corner of the internet continue sharing these soothing scientific adventures with curious minds like yours. And if you're feeling chatty, please let me know in the comments where in the world you're listening from and what time it is in your corner of the universe. I love picturing our little constellation of sleepy thinkers scattered across time zones, from cozy bedrooms in midnight London to quiet apartments in evening San Francisco, all connected by our shared fascination with the impossible physics that governs everything we touch and see. This video is here to relax you, to enchant you just enough to make your thoughts drift like quantum particles through the landscape of possibility. You won't need to memorize formulas or solve equations, just float with me as we explore how reality might be far stranger and more wonderful than we ever dared imagine, how the solid world around you is mostly empty space filled with probability waves, and how the universe might be writing itself into existence one observation at a time. And just before we begin our quantum adventure, this video is designed for relaxation and education. It is not academic instruction or a substitute for proper physics courses. Always take care of yourself, and may your quantum dreams be both probable and peaceful. Let's start with something that sounds almost too simple to be revolutionary. You're lying there, comfortable and ready for sleep, surrounded by what feels like a solid, predictable world. Your pillow supports your head, your blanket wraps around your body, the floor holds up your bed. Everything seems so thoroughly, reassuringly real. But hold that thought gently because, as it turns out, the solid matter you're resting on is mostly empty space, and the particles that make up what little substance there is don't quite exist in the way you might think they do. Quantum mechanics is the branch of physics that describes the behavior of matter and energy at the smallest possible scales, where the normal rules that govern basketballs and buildings and planets simply stop working. It's a realm where particles can be in multiple places simultaneously, where information can travel instantly across vast distances, and where the act of looking at something fundamentally changes what you're looking at. It sounds like science fiction, but it's the most precisely tested and universally applicable theory in the history of science. The story begins in the early 1900s, when physicists started noticing that light and matter behaved very strangely when examined closely enough. They discovered that energy comes in discrete little packets called quanta, hence the name quantum mechanics. But what they found wasn't just a technical curiosity for laboratory experiments. They found that reality itself operates according to principles that defy everything our everyday experience tells us about how the world works. Think of a coin spinning in the air. In our normal experience, the coin is either heads or tails at any given moment during its flight. We just don't know which until we catch it and look. But quantum particles are more like magical coins that are actually both heads and tails simultaneously while they're spinning, only deciding which they are when someone finally catches them and takes a peek. This isn't just our ignorance about hidden information. The particle genuinely exists in what physicists call a superposition of all possible states until the moment of observation collapses it into one definite outcome. But there's so much more strangeness to explore in this quantum landscape. Let's delve deeper into what it means for something to exist in multiple states at once, because this concept reaches into every aspect of how quantum systems behave and challenges everything we thought we knew about the nature of existence itself. Consider the electron, one of the fundamental building blocks of all matter. In the world described by quantum mechanics, an electron doesn't orbit the nucleus of an atom like a tiny planet circling a miniature sun. Instead, it exists as a cloud of probability, simultaneously occupying every possible position around the nucleus until something forces it to manifest in a specific location. It's not that we don't know where the electron is, it's that the electron genuinely doesn't have a definite position until we measure it. Imagine trying to describe the location of a musical note. Where exactly does middle C exist when you play it on a piano? Is it in the vibrating string, in the moving air, in your ear, in your brain? The note exists as a wave pattern distributed through space and time, only becoming localized when it interacts with something that can detect and interpret it. Electrons behave similarly, existing as waves of probability that fill space until they interact with something that forces them to become particle-like. This wave-particle duality is one of the most beautiful and puzzling aspects of quantum mechanics. Light behaves like a wave when we're not paying attention to individual photons, creating interference patterns and flowing around obstacles the way water waves ripple across a pond. But shine that same light on a detector that can count individual particles, and suddenly light behaves like a stream of discrete energy packets, each one hitting the detector in a specific location at a specific time. The truly mind-bending part is that this behavior depends on how we choose to observe the system. If we set up an experiment designed to detect wave-like properties, we get wave-like results. If we set up an experiment designed to detect particle-like properties, we get particle-like results. It's as though the universe is responding to our questions by deciding what kind of reality to present to us. This leads us to one of the most famous and counterintuitive concepts in all of physics, the measurement problem. According to quantum mechanics, particles exist in superposition, occupying all possible states simultaneously until the moment they're observed. But what exactly counts as observation? Does it require a conscious observer, or does any interaction with the environment count as measurement? Let's explore this through the lens of the most famous thought experiment in physics, Schrödinger's cat. Austrian physicist Erwin Schrödinger proposed this scenario in 1935 to illustrate what he saw as the absurdity of applying quantum mechanics to everyday objects. Imagine a cat sealed in a box with a Geiger counter, a radioactive atom, a hammer, and a flask of poison. The radioactive atom has a 50% chance of decaying within 1 hour. If it decays, the Geiger counter detects the radiation and triggers the hammer to break the flask, releasing poison that kills the cat. If the atom doesn't decay, the cat remains alive. According to quantum mechanics, before we open the box, the radioactive atom exists in a superposition of decayed and not decayed states. This means the entire system, including the cat, should also exist in a superposition of alive and dead states until we observe it. The cat would be neither alive nor dead, but both simultaneously, until the moment we lift the lid and force reality to choose. Schrödinger intended this as a criticism of quantum mechanics, pointing out that cats are obviously either alive or dead, never both. But instead of discrediting quantum theory, the thought experiment highlighted one of the deepest mysteries in physics. How does the quantum world of superposition and probability connect to the classical world of definite outcomes and everyday experience? Speaking of everyday experience, there's something quietly profound about the fact that you're experiencing a definite classical reality right now while being made entirely of quantum particles. Every atom in your body, every photon hitting your retina, every electrical signal in your nervous system operates according to quantum mechanical principles. Yet somehow, all of this quantum weirdness adds up to create the solid, predictable world you experience. This is the puzzle of quantum decoherence, the process by which quantum systems lose their superposition and become classical through interaction with their environment. Your body is constantly interacting with countless particles and fields, each interaction serving as a kind of measurement that collapses quantum states into definite outcomes. The warm air around you, the electromagnetic fields from electronic devices, the cosmic radiation streaming down from space. All of these serve to decohere quantum systems and create the classical reality you experience. But even in this classical reality, quantum effects are everywhere if you know how to look for them. The stability of atoms depends on quantum mechanics. Without the quantum mechanical property called electron spin, The periodic table wouldn't work and complex molecules couldn't form. The nuclear fusion that powers the sun requires quantum tunneling, a process where particles pass through energy barriers that should be impossible to cross in classical physics. Let's take a closer look at quantum tunneling, because it's one of the most beautiful examples of how quantum mechanics enables processes that would be impossible in our everyday experience. Imagine rolling a ball up a hill. In classical physics, if the ball doesn't have enough energy to reach the top, it will simply roll back down. But in quantum mechanics, there's a probability that the ball could tunnel through the hill and appear on the other side, even if it doesn't have enough energy to go over the top. This isn't just a mathematical curiosity. Quantum tunneling happens constantly in your body. The nuclear fusion reactions that created the heavy elements in your bones and blood depend on protons tunneling through the electromagnetic barriers that separate atomic nuclei. Without quantum tunneling, stars couldn't shine, and the universe would be a cold, dark place filled only with hydrogen and helium. Your computer or smartphone operates using quantum tunneling as well. The transistors that process information are so small that electrons regularly tunnel through the barriers that are supposed to control their flow. Engineers have learned to harness this quantum behavior to create faster and more efficient electronic devices. In a very real sense, you're reading these words because of the strange quantum property that allows particles to be in places they shouldn't be able to reach. But there's an even stranger quantum phenomenon that connects particles across vast distances in ways that seem to violate everything we know about space and time. This is quantum entanglement, what Einstein famously called spooky action at a distance. When two particles become entangled, measuring the properties of one instantly affects the properties of the other, no matter how far apart they are. Let's explore entanglement through a simple example. Imagine two coins that are quantum mechanically entangled. Before you flip either coin, each exists in a superposition of heads and tails, but these aren't independent superpositions. The coins are correlated in such a way that if one shows heads when measured, the other will always show tails, and vice versa. The strange part is that this correlation is maintained instantaneously, even if the coins are on opposite sides of the universe. When you flip the first coin and it comes up heads, somehow the second coin immediately knows to show tails, faster than light could travel between them. This isn't because they're sending signals to each other. Instead, they remain connected through what physicists call non-local correlation, a fundamental feature of quantum mechanics that Einstein never fully accepted, but that experiments have confirmed again and again. This quantum entanglement is more than just a curiosity for physics laboratories. It's the foundation for emerging technologies like quantum computing and quantum cryptography. Quantum computers use entangled particles to perform calculations that would be impossible for classical computers, potentially solving problems that would take traditional computers longer than the age of the universe. Meanwhile, quantum cryptography uses entanglement to create communication systems that are fundamentally secure. Any attempt to eavesdrop on an entangled communication channel necessarily disturbs the quantum states being used to encode the message, immediately alerting the legitimate parties that their communication has been compromised, its security guaranteed by the laws of physics themselves. But here's where things get even more fascinating. Recent experiments have shown that entanglement isn't limited to pairs of particles. Scientists have created entangled systems involving dozens, hundreds, even thousands of particles, all connected through quantum correlations that transcend classical ideas about locality and separateness. Some physicists speculate that entanglement might be a fundamental feature of reality, connecting everything in the universe through an invisible web of quantum correlations. This brings us to one of the most profound and contentious questions in modern physics. If quantum mechanics describes fundamental reality, and if quantum systems exist in superposition until observed, what does this tell us about the nature of reality itself? Are there multiple parallel universes corresponding to each possible outcome of every quantum measurement? Does consciousness play a special role in collapsing quantum states? Or is there some deeper level of reality that we haven't discovered yet? The many worlds interpretation of quantum mechanics, first proposed by Hugh Everett in 1957, suggests that every quantum measurement splits the universe into multiple branches, each corresponding to a different possible outcome. In this view, Schrödinger's cat is both alive and dead, but in different branches of reality. We only experience one branch, but all the others are equally real and continue to evolve according to their own quantum mechanical laws. This interpretation eliminates the measurement problem by saying that superposition never actually collapses. Instead, conscious observers become entangled with the systems they're observing, and each branch of the universal wave function contains observers who see definite outcomes. It's an elegant solution to the conceptual problems of quantum mechanics, but it comes at the cost of an infinity of parallel universes that we can never directly observe or interact with. Other interpretations take different approaches to the puzzle of quantum reality. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that quantum mechanics is complete as it stands, and that asking about the reality underlying quantum phenomena is meaningless. In this view, the wave function is simply a tool for calculating probabilities, not a description of objective reality. The pilot wave theory, originally developed by Louis de Broglie and later refined by David Bohm, proposes that particles do have definite positions and velocities, but they're guided by a quantum field that creates the appearance of wave-like behavior and quantum randomness. This interpretation preserves classical realism, but requires accepting the existence of a mysterious guiding field that connects all particles instantaneously. Each interpretation offers a different picture of what quantum mechanics tells us about the nature of reality. But regardless of which interpretation you prefer, they all agree on the experimental predictions of quantum theory, and those predictions have been confirmed with extraordinary precision in countless experiments over more than a century. Let's take a moment to appreciate just how precisely quantum mechanics has been tested. Some quantum mechanical predictions have been verified to better than 1 part in 10 billion, making quantum mechanics one of the most accurate theories in the history of science. The magnetic moment of the electron, for example, has been measured to agree with quantum mechanical calculations to more than 10 decimal places. This extraordinary precision isn't just an academic achievement, it's the foundation for technologies that have transformed human civilization. Lasers work because of the quantum mechanical properties of atoms and photons. Magnetic resonance imaging uses quantum mechanical spin to peer inside the human body without surgery. Global positioning satellites require corrections for quantum mechanical effects to maintain their accuracy. The computer or phone you're using to read this operates using quantum mechanical principles in its semiconductors. The LED lights in your room, the solar panels on rooftops, the fiber optic cables that carry internet signals around the world all depend on our understanding of quantum mechanics. In a very real sense, the modern world is built on a foundation of quantum strangeness. But perhaps the most beautiful aspect of quantum mechanics isn't its technological applications, but the way it reveals the fundamental interconnectedness of reality. Quantum entanglement shows us that separated particles can remain correlated in ways that transcend classical notions of space and time. The uncertainty principle tells us that perfect knowledge and perfect control are impossible, that there's always an element of mystery and unpredictability at the heart of nature. The uncertainty principle, formulated by Werner Heisenberg in 1927, states that there are fundamental limits to how precisely we can know certain pairs of properties simultaneously. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This isn't a limitation of our measuring instruments, it's a fundamental feature of quantum systems. Think of it like trying to photograph a hummingbird. If you use a fast shutter speed to freeze its motion and see exactly where it is, you lose information about how fast it was moving and in which direction. If you use a slow shutter speed to capture its motion, you get a blurred image that shows the bird's trajectory but not its precise position. The uncertainty principle tells us that this trade-off between position and momentum information is built into the fabric of reality itself. This fundamental uncertainty has profound implications for how we understand causality and determinism. In classical physics, if you knew the exact position and velocity of every particle in the universe, you could in principle calculate the entire future and past of the cosmos. The universe would be like a vast clockwork mechanism, complex but ultimately predictable. Quantum mechanics tells us that this kind of perfect predictability is impossible, not because we lack sufficient computing power, but because the information required for such predictions doesn't exist. The future is genuinely open, influenced by but not completely determined by the present. There's room in the quantum world for novelty, creativity, and genuine surprise. This openness in quantum systems might even be connected to the existence of consciousness and free will, though the connections are speculative and controversial. Some physicists and philosophers have suggested that the quantum mechanical collapse of wave functions might provide a physical mechanism for mental causation, allowing consciousness to influence physical events in ways that wouldn't be possible in a purely deterministic classical world. The relationship between quantum mechanics and consciousness remains one of the deepest unsolved problems in science. Does consciousness cause wave function collapse, as some interpretations suggest? Or does consciousness emerge from quantum processes in the brain? Or are consciousness and quantum mechanics completely separate phenomena that just happen to both involve mystery and observer effects? Roger Penrose and Stuart Hameroff have proposed that consciousness arises from quantum processes in microscopic structures called microtubules inside brain cells. Their theory suggests that the brain operates as a quantum computer, using superposition and entanglement to process information in ways that classical computers cannot. While this theory remains controversial and largely unproven, it illustrates how quantum mechanics might be involved in the most profound aspects of human experience. Meanwhile, other researchers study quantum biology, the emerging field that explores quantum effects in living systems. They've discovered that photosynthesis, the process that converts sunlight into chemical energy in plants, uses quantum coherence to achieve nearly perfect efficiency in energy transfer. Birds might use quantum entanglement in specialized proteins in their eyes to navigate using the Earth's magnetic field. Some scientists even speculate that the sense of smell works by detecting quantum vibrations in odor molecules. These discoveries suggest that life itself might be fundamentally quantum mechanical. The warm, wet, noisy environment inside living cells was long thought to be too chaotic to support quantum effects, but it appears that evolution has found ways to harness quantum phenomena for biological advantage. Perhaps consciousness, that most mysterious aspect of our existence, is also a quantum phenomenon. But let's step back from these speculative connections and explore another fundamental aspect of quantum mechanics that affects every atom in your body. This is the concept of quantum fields, the deeper reality from which particles emerge like waves on an ocean. In quantum field theory, particles aren't fundamental objects but rather excitations in underlying fields that fill all of space. The electron is an excitation in the electron field, the photon is an excitation in the electromagnetic field, and so on for all the particles in the standard model of physics. Even empty space isn't truly empty but filled with quantum fields fluctuating at the quantum level. These quantum field fluctuations have measurable effects. The Casimir effect, first predicted in 1948 and later confirmed experimentally, shows that two metal plates placed very close together in a vacuum will experience a small attractive force due to quantum fluctuations in the electromagnetic field. Virtual particles continuously appear and disappear in the space between the plates, and the restricted geometry changes the energy of these fluctuations in a way that pulls the plates together. This might sound like an obscure laboratory curiosity, but quantum field fluctuations play crucial roles in many physical processes. They contribute to the anomalous magnetic moment of the electron. They drive the expansion of the universe during cosmic inflation, and they might even be responsible for the existence of matter itself through a process called spontaneous symmetry breaking. The Higgs mechanism, confirmed by the discovery of the Higgs boson in 2012, shows how particles acquire mass through their interaction with a field that fills all of space. The Higgs field gives mass to fundamental particles, the way honey gives resistance to movement, by interacting with particles as they move through space. Without the Higgs field, electrons and quarks would be massless and atoms couldn't form. These quantum fields extend throughout the universe, connecting every region of space through their quantum fluctuations and correlations. In a sense, the entire cosmos is a single interconnected quantum system, with local events connected to distant regions through non-local quantum correlations. The boundaries between here and there, between self and other, become fuzzy when viewed through the lens of quantum field theory. This universal interconnectedness through quantum fields might explain some of the strange correlations observed in quantum experiments. When two particles become entangled, they're not really separate objects connected by some mysterious faster-than-light communication. Instead, they're aspects of a single quantum system described by a unified wave function. The apparent separateness is an illusion created by a classical perspective on a fundamentally quantum reality. But even as quantum mechanics reveals the interconnected nature of reality, it also preserves a fundamental role for randomness and unpredictability. Quantum systems don't just appear random because we lack information about hidden variables. According to most interpretations of quantum mechanics, the randomness is genuine and irreducible. When a radioactive nucleus decays, there's no deeper cause that determines exactly when the decay will occur. The timing is fundamentally random, governed only by probabilities calculated from the quantum wave function. This isn't ignorance about hidden clockwork, it's genuine indeterminacy built into the structure of physical law. This quantum randomness serves as a source of true novelty in the universe. Each quantum measurement creates genuine new information that wasn't contained in the previous state of the system. Over billions of years and countless quantum events, this accumulation of genuinely new information might be responsible for the complexity and creativity we observe in the natural world. The second law of thermodynamics tells us that isolated systems tend toward increasing entropy and decreasing organization. But quantum measurements can create new information and new correlations, potentially driving increases in complexity that seem to violate the classical understanding of entropy. Life itself might be a manifestation of this quantum creativity, using quantum processes to create order and information in apparent violation of classical thermodynamics. This brings us to one of the most fascinating frontiers in modern physics, the study of quantum information and quantum computation. Information, it turns out, is not just an abstract concept, but a physical quantity with the same fundamental status as mass and energy. Quantum systems can store and process information in ways that are impossible for classical systems, leading to potentially revolutionary advances in computing, communication, and our understanding of physical law. A classical computer bit can be either 0 or 1, but a quantum bit or qubit can exist in a superposition of 0 and 1 simultaneously. This allows a quantum computer with just 300 qubits to represent more states than there are atoms in the observable universe. Quantum computers don't just process information faster, they process it in a fundamentally different way that allows them to solve certain problems that are intractable for any conceivable classical computer. The most famous application is Shor's algorithm for factoring large numbers, which would allow quantum computers to break most current encryption systems. But quantum computers might also revolutionize chemistry by simulating molecular interactions that are too complex for classical computers, leading to new drugs, materials, and catalysts. They might solve optimization problems that could improve everything from traffic flow to financial modeling. But perhaps the most profound application of quantum information theory is in understanding the universe itself. Some physicists propose that reality is fundamentally informational, that matter and energy are just different ways of processing and storing quantum information. In this view, the universe is essentially a vast quantum computer, constantly calculating its own next state through the interactions of quantum fields and particles. This informational view of reality suggests deep connections between physics, mathematics, and computation. The holographic principle in cosmology proposes that all the information contained in a volume of space can be encoded on its two-dimensional boundary, like a hologram. Black holes might be information processing systems, with their entropy proportional to the area of their event horizons rather than their volume. These ideas are still speculative, but they point toward a future understanding of physics where information plays a central role alongside space, time, and matter. Just as Einstein showed us that space and time are aspects of a unified space-time, and just as quantum mechanics revealed the wave-particle duality of matter and energy, future physics might reveal information, matter, and geometry as different aspects of a deeper quantum reality. While we're exploring the implications of quantum mechanics for our understanding of reality, let's consider how these ideas might affect our everyday lives and personal perspectives. Living in a quantum universe means accepting fundamental uncertainty and interconnectedness as basic features of existence. The solid, separate objects of classical physics give way to probability waves and quantum correlations that transcend traditional boundaries. This might seem abstract and removed from daily experience, but consider how quantum mechanics affects your relationship with time and causality. In the classical world, causes precede effects in a clear temporal order, but quantum mechanics allows for subtler causal relationships where the future can influence the present through quantum correlations, and where measurement choices can retroactively determine the properties of quantum systems. Delayed choice experiments, variations of the famous double-slit experiment, show that decisions made about how to observe a quantum system can apparently affect the past behavior of that system. For a photon's wave-like or particle-like nature can be determined by measurement choices made after the photon has already interacted with a screen, suggesting that the present has a kind of backwards influence on the past. This doesn't mean you can change history or send messages to yesterday, but it does suggest that the relationship between past, present, and future is more subtle and interconnected than our everyday experience suggests. Time might not be the simple forward-flowing river we imagine, but something more like an ocean where currents flow in multiple directions and distant events can influence each other through quantum correlations. Similarly, quantum entanglement challenges our everyday notions of separateness and independence. If fundamental particles can remain correlated across arbitrary distances, what does this mean for our sense of individual identity and autonomy? Are we truly separate beings, or are we all aspects of a deeper quantum system that includes the entire universe? These questions don't have definitive answers, but they invite us to consider our place in a universe that is far stranger and more interconnected than classical physics suggested. The quantum world is not just a realm of abstract mathematics and laboratory experiments. It's the deeper reality that underlies everything we experience and everything we are. As you lie there ready for sleep, consider that every atom in your body was forged in the quantum furnaces of ancient stars, held together by quantum forces, animated by quantum processes that enable the chemistry of life. The thoughts moving through your mind might themselves be quantum phenomena, emerging from the quantum interactions of molecules in your neural networks. The light that illuminated your day came from quantum fusion reactions in the sun, travelled through space as quantum fields, and was absorbed by quantum processes in your retina. The solid bed supporting you is mostly empty space held together by quantum forces between atoms that exist as probabilities clouds rather than definite objects. Even your breathing involves quantum processes. The oxygen molecules you inhale undergo quantum mechanical interactions as they bind to hemoglobin in your blood. The cellular respiration that powers your body depends on quantum effects in the electron transport chains of your mitochondria. Life itself is a quantum phenomenon, using the strange properties of quantum systems to create order and complexity in an otherwise entropic universe. But perhaps, most remarkably, your consciousness, your ability to experience and contemplate these quantum mysteries, might itself be quantum mechanical. The integration of information across different regions of your brain, the unity of conscious experience that binds together sensations, thoughts, and memories into a coherent sense of self, might depend on quantum correlations that transcend the classical boundaries between different neural systems. This doesn't mean that consciousness is supernatural, or that quantum mechanics validates mystical beliefs about the mind. Instead, it suggests that consciousness is a natural phenomenon that emerges from the quantum processes that govern all physical systems. You're not separate from the quantum universe you're contemplating. You're an expression of it, a way the universe has of knowing and experiencing itself. The history of quantum mechanics is also the history of human beings grappling with ideas that challenge our most basic assumptions about reality. From Max Planck's reluctant introduction of the quantum hypothesis to solve the black body radiation problem, to Einstein's Nobel Prize-winning explanation of the photoelectric effect, to Heisenberg's matrix mechanics and Schrödinger's wave equation, quantum theory emerged through the work of brilliant minds trying to understand experimental results that made no sense according to classical physics. These scientists weren't trying to overthrow common sense or create a mysterious theory that would confuse future generations of students. They were simply following the experimental evidence wherever it led, even when it led to conclusions that seemed impossible or absurd. The strangeness of quantum mechanics isn't a flaw in the theory, it's a reflection of how strange reality actually is at its deepest levels. Werner Heisenberg once wrote that what we observe is not nature itself, but nature exposed to our method of questioning. Quantum mechanics might not tell us what reality is, but it tells us how reality responds when we try to measure and observe it. The observer effect, the measurement problem, and the interpretational puzzles of quantum theory might be telling us something profound about the relationship between knowledge and reality, between the knower and the known. Perhaps the most important lesson of quantum mechanics is humility. For all our technological achievements and mathematical sophistication, we still don't fully understand the nature of the reality we inhabit. Quantum mechanics works with extraordinary precision, but its conceptual foundations remain mysterious and controversial more than a century after its discovery. This ongoing mystery isn't a failure of science, but one of its greatest gifts. Science at its best doesn't just give us answers, it gives us better questions. Quantum mechanics has opened up new realms of wonder and possibility, from parallel universes to consciousness studies to quantum technologies that might transform civilization. As quantum computers become more powerful and quantum technologies become more widespread, we might find ourselves living in an increasingly quantum world where superposition and entanglement are not just abstract concepts, but practical tools for communication, computation, and exploration. The same quantum principles that seem so strange and counterintuitive might become as familiar and useful as electricity or radio waves. But even as we harness quantum phenomena for practical applications, the deeper mysteries remain. What is the nature of quantum measurement? How does the quantum world give rise to classical experience? What role, if any, does consciousness play in the collapse of wave functions? Are there hidden variables underlying quantum phenomena, or is quantum randomness fundamental? These questions continue to drive research in foundations of quantum mechanics, quantum gravity, and quantum information theory. Future discoveries might resolve some of these puzzles, but they're likely to reveal new mysteries as deep and strange as those we face today. The history of physics suggests that each answer opens up new questions. Each new understanding reveals deeper layers of mystery. The quantum mechanical description of reality includes elements that seem almost magical: particles that tunnel through barriers, information that travels instantly across vast distances, measurements that retroactively determine the properties of physical systems. But this apparent magic is simply how nature actually works when examined closely enough. The magic isn't in our theories, it's in the reality our theories describe. This realization can be both humbling and exhilarating. On one hand, it shows how much we still don't understand about the universe we inhabit. On the other hand, it reveals that reality is far more interesting and creative than our everyday experience suggests. We live in a universe where the impossible happens routinely at microscopic scales, where the boundaries between existence and possibility are blurred, where consciousness might play a fundamental role in the structure of physical law. The implications extend beyond physics into philosophy, neuroscience, and even spirituality. If quantum mechanics tells us that reality is fundamentally uncertain, interconnected, and observer-dependent, what does this mean for ethics, politics, and human relationships? How should we live in a quantum universe where separateness might be an illusion, and where the future is genuinely open rather than predetermined? These are not questions that physics can answer definitively, but they are questions that a quantum mechanical worldview makes impossible to ignore. Just as Darwin's theory of evolution changed how we think about human nature and our place in the living world, quantum mechanics might change how we think about consciousness, free will, and our relationship to the cosmos. The transition from classical to quantum thinking might represent a fundamental shift in human consciousness, comparable to the transition from mythological to rational thinking that occurred in ancient Greece, or the transition from geocentric to heliocentric cosmology during the scientific revolution. We might be in the early stages of learning to think quantum mechanically, to see reality in terms of probability waves and quantum correlations, rather than solid objects and deterministic laws. This quantum worldview doesn't diminish the importance of classical physics or everyday experience. Classical mechanics remains an excellent approximation for describing the motion of planets, the flight of baseballs, and the operation of most machines. But quantum mechanics reveals that classical physics is a limited case of a deeper, stranger reality that operates according to principles we're only beginning to understand. The coexistence of quantum and classical descriptions might teach us something important about the nature of truth and scientific knowledge. Perhaps reality is too rich and complex to be captured by any single theoretical framework. Perhaps we need multiple complementary perspectives, each revealing different aspects of a reality that transcends any particular way of looking at it. Niels Bohr's principle of complementarity suggests that quantum systems can be described equally validly as particles or waves, but never both simultaneously. The choice of description depends on how we choose to observe the system. Perhaps this principle applies more broadly, suggesting that reality itself has a complementary structure that requires multiple perspectives for complete understanding. This idea resonates with ancient philosophical traditions that emphasize the limitations of conceptual thinking and the need for direct experience to apprehend truth. But quantum mechanics adds a scientific dimension to these insights, showing how the observer and the observed are interconnected in ways that classical physics never imagined. The practical applications of quantum mechanics continue to expand as our understanding deepens and our technology improves. Quantum sensors can detect gravitational waves from colliding black holes billions of light years away. Quantum communication systems provide theoretically perfect security for sensitive information. Quantum simulators might help us understand high-temperature superconductivity and design room-temperature superconductors that could revolutionize energy transmission and storage. Future quantum technologies might include quantum artificial intelligence systems that process information in fundamentally new ways, quantum medical imaging systems that can see inside living cells without damaging them, and quantum materials with properties that seem impossible according to classical physics. We might even develop quantum transportation systems that use quantum tunneling or teleportation to move people and objects in ways that transcend current limitations. But perhaps the most significant impact of quantum mechanics will be on human consciousness and culture. As quantum thinking becomes more widespread and quantum technologies become more common, we might develop new ways of understanding ourselves and our relationship to reality. The quantum worldview might lead to new forms of art, literature, and music that explore themes of uncertainty, interconnectedness, and observer participation in reality. Quantum mechanics might also influence how we approach problems in other fields. Quantum principles like superposition and entanglement might provide new models for understanding complex systems in biology, psychology, and sociology. The quantum concept of measurement might offer new insights into how observation and participation affect social and psychological processes. Educational systems might evolve to teach quantum thinking alongside classical logic, helping students develop comfort with uncertainty, paradox, and multiple simultaneous perspectives. Business and organizational theory might incorporate quantum concepts like coherence and decoherence to understand how groups maintain focus while adapting to changing environments. The quantum mechanical understanding of information as a fundamental aspect of reality might revolutionize computer science, artificial intelligence, and cognitive science. If consciousness emerges from quantum information processing in the brain, then understanding quantum mechanics might be essential for understanding the mind itself. But even as we speculate about these future applications and implications, it's worth remembering that quantum mechanics has already transformed human civilization in ways that most people don't fully appreciate. The electronic devices that surround us, the medical technologies that extend our lives, the communication systems that connect us across vast distances, all depend on our understanding of quantum phenomena. The laser that reads information from optical disks uses stimulated emission, a quantum mechanical process where photons encourage atoms to emit identical photons in perfect synchronization. The global positioning system that helps us navigate depends on atomic clocks that use quantum mechanical transitions in cesium atoms to measure time with extraordinary precision. The magnetic resonance imaging machines that peer inside our bodies without surgery detect quantum mechanical signals from hydrogen nuclei in water molecules. These technologies work because physicists and engineers learn to harness quantum phenomena for practical purposes, even while the deeper mysteries of quantum mechanics remained unsolved. We don't need to understand consciousness or parallel universes to build quantum computers or quantum communication systems. We just need to understand how quantum systems behave and how to control their behavior for useful purposes. This pragmatic approach to quantum mechanics reflects a broader truth about science and technology. We often learn to use natural phenomena long before we fully understand them. Humans used fire for hundreds of thousands of years before understanding combustion. We used electricity for decades before understanding electromagnetic theory. We're now using quantum mechanics to build revolutionary technologies while still debating what it tells us about the nature of reality. But the practical applications of quantum mechanics do provide clues about its deeper meaning. The fact that quantum computers can solve certain problems exponentially faster than classical computers suggests that quantum mechanics taps into computational resources that are hidden from classical physics. The many worlds interpretation explains this by suggesting that quantum computers perform calculations in parallel across multiple branches of reality. Similarly, the perfect security provided by quantum cryptography suggests that quantum correlations really are fundamentally different from classical correlations. The no-cloning theorem, which states that arbitrary quantum states cannot be perfectly copied, provides the theoretical foundation for quantum cryptographic security. This theorem reflects a deep truth about information in quantum mechanics that has no classical analogue. The study of quantum error correction, essential for building practical quantum computers, has revealed surprising connections between quantum mechanics and geometry, topology, and even black hole physics. Quantum error-correcting codes use the same mathematical structures that describe the geometry of curved spacetime and the information paradoxes of black holes. These connections hint at even deeper relationships between quantum mechanics, gravity, and the structure of spacetime itself. Some physicists propose that space and time emerge from more fundamental quantum mechanical processes, that the geometry of the universe is somehow encoded in patterns of quantum entanglement that span cosmic scales. The holographic principle in cosmology suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. This principle, originally discovered in the context of black hole physics, might apply to the entire observable universe. If so, the three-dimensional space we experience might be a kind of holographic projection of information encoded on a distant two-dimensional surface. These ideas remain highly speculative, but they illustrate how quantum mechanics continues to challenge our most basic assumptions about the nature of space, time, and reality. Just as quantum mechanics revolutionized our understanding of atoms and molecules, it might eventually revolutionize our understanding of the cosmos itself. The search for a quantum theory of gravity, the holy grail of modern theoretical physics, represents an attempt to reconcile quantum mechanics with Einstein's general theory of relativity. Both theories are extraordinarily successful within their respective domains, but they make contradictory predictions about the behavior of matter and energy in extreme conditions, such as the interiors of black holes or the first moments after the Big Bang. String theory, loop quantum gravity, and other approaches to quantum gravity each offer different visions of how space-time and matter might emerge from more fundamental quantum mechanical processes. In string theory, particles are vibrations of tiny strings existing in 10 or 11 dimensions. In loop quantum gravity, space itself has an atomic structure at the smallest scales, with discrete units of area and volume. These theories remain unproven and might never be directly testable, but they represent humanity's ongoing attempt to understand the deepest levels of physical reality. They show how quantum mechanics continues to drive scientific discovery more than a century after its initial development, opening up new realms of possibility that previous generations couldn't imagine. The philosophical implications of quantum mechanics extend far beyond physics into questions about the nature of knowledge, reality, and consciousness that have puzzled thinkers for millennia. The measurement problem in quantum mechanics echoes ancient philosophical questions about the relationship between appearance and reality, between what we observe and what actually exists. Plato's allegory of the cave suggested that ordinary experience provides only shadows of true reality. quantum mechanics might be telling us something similar, that the classical world of definite objects and properties is like a shadow cast by a deeper quantum reality that operates according to very different principles. The role of the observer in quantum mechanics raises questions about the relationship between mind and matter that philosophers have debated since ancient times. Does consciousness create reality through observation, as some interpretations of quantum mechanics suggest? Or does reality exist independently of observation, with consciousness simply revealing pre-existing facts about the world? These questions don't have definitive scientific answers, but quantum mechanics provides new ways of thinking about them. The participatory universe described by physicist John Wheeler suggests that observers don't just discover reality, but participate in its creation through their choices about what to observe and how to observe it. This participatory view of reality resonates with indigenous wisdom traditions that emphasize the interconnectedness of observer and observed, knower and known. But quantum mechanics gives these ancient insights a rigorous scientific foundation, showing how observer participation might be built into the fundamental structure of physical law. The quantum mechanical understanding of reality is fundamentally relational, existing in the relationships between systems rather than in the systems themselves, also echoes philosophical traditions that emphasize the interdependence of all phenomena. Buddhism's concept of dependent origination, which holds that all phenomena arise in dependence upon causes and conditions, bears striking similarities to the quantum mechanical view that properties emerge through interaction rather than existing independently. These philosophical connections don't prove that quantum mechanics validates any particular spiritual or metaphysical worldview, but they do suggest that the quantum revolution in physics might be part of a broader shift in human consciousness towards more relational and participatory ways of understanding reality. The implications for ethics and human relationships are profound. If quantum mechanics tells us that separateness is an illusion and that all systems are fundamentally interconnected, how should this affect how we treat each other and the environment? If the future is genuinely open rather than predetermined, what does this mean for personal responsibility and social change? These questions don't have simple answers, but they illustrate how scientific discoveries can influence moral and spiritual perspectives. The mechanistic worldview of classical physics supported attitudes of domination and exploitation based on the assumption that humans are separate from and superior to the rest of nature. A quantum mechanical worldview might support attitudes of cooperation and care based on recognition of fundamental interconnectedness. The uncertainty principle might also have ethical implications. If perfect knowledge and control are impossible, perhaps we need to cultivate humility and acceptance rather than trying to dominate and predict everything. The quantum mechanical understanding that measurement inevitably disturbs the system being measured might teach us to approach relationships and social situations with greater sensitivity and awareness of our impact on others. But these applications of quantum mechanics to human affairs require great care and critical thinking. The history of science is littered with premature attempts to apply new scientific theories to social and psychological phenomena without adequate justification. Quantum mechanics describes the behavior of atoms and subatomic particles under carefully controlled laboratory conditions. Extending these insights to human consciousness and social relationships requires additional evidence and argumentation that goes beyond physics itself. Nevertheless, the quantum mechanical worldview does provide a useful counterpoint to reductionist materialism and mechanical determinism. It shows that, even at the level of fundamental physics, reality is more mysterious, creative, and open-ended than classical science suggested. This openness provides conceptual space for phenomena like consciousness, free will, and creativity that seem difficult to explain in purely mechanistic terms. The ongoing development of quantum technologies will likely make these philosophical questions increasingly practical and urgent. As quantum computers become more powerful and quantum artificial intelligence systems become possible, we might need to grapple seriously with questions about the relationship between information processing and consciousness, between computation and understanding. If quantum mechanics really is connected to consciousness in some fundamental way, then quantum computers might develop forms of artificial consciousness that differ qualitatively from classical artificial intelligence. This possibility raises profound questions about the rights and moral status of artificial quantum minds, about the nature of suffering and well-being in artificial systems, and about the future relationship between human and artificial intelligence. These speculations might seem far-fetched, but they illustrate how quantum mechanics continues to challenge our assumptions and open up new possibilities for understanding ourselves and our place in the universe. The quantum revolution is not just about technology or scientific theory, it's about the evolution of human consciousness and our relationship with reality itself. As you drift towards sleep tonight, surrounded by the quantum field fluctuations that fill all of space, supported by quantum forces that hold matter together, breathing oxygen that underwent quantum processes in distant stars, consider the remarkable journey that brought humanity to this point of understanding. From our ancestors who first looked up at the night sky and wondered about their place in the cosmos, to the modern physicists who discovered that reality itself is far stranger than anyone imagined, we are part of an ongoing story of discovery and wonder. The atoms in your body are quantum mechanical systems that have existed since the early universe, recycled through countless stars and planets and living beings before becoming part of you. The quantum correlations that connect particles across vast distances might connect you to the furthest reaches of the cosmos in ways we're only beginning to understand. Your thoughts and dreams tonight will emerge from quantum processes in your brain, patterns of information processing that might tap into the same quantum computational resources that power quantum computers. The boundary between your inner world of consciousness and the outer world of quantum fields and particles might be less clear than you imagine. But even if consciousness is quantum mechanical, it doesn't become less mysterious or less precious. Instead, it reveals that mystery and preciousness are built into the fundamental structure of reality. You're not just an observer of the quantum universe, you're a participant in its ongoing creation, a way the cosmos has of knowing and experiencing itself. The future will likely bring new quantum technologies that transform human civilization in ways we can barely imagine. Quantum computers might solve problems that revolutionize medicine, materials science, and artificial intelligence. Quantum communication networks might connect minds across vast distances in forms of intimacy and understanding that transcend current limitations. Quantum sensors might reveal new layers of reality that we haven't yet discovered. But perhaps the most important gift of quantum mechanics is not technological, but philosophical and spiritual. It reminds us that reality is far more mysterious, creative, and interconnected than our everyday experience suggests. It invites us to embrace uncertainty not as a limitation, but as an opening to genuine novelty and surprise. It suggests that consciousness and observation might play fundamental roles in the ongoing creation of reality. The journey into quantum mechanics is ultimately a journey into the deepest nature of existence itself. It's a reminder that science at its best is not just about accumulating facts and building technologies, but about cultivating wonder and maintaining openness to mystery. The quantum world is not just strange, it's beautiful in its strangeness, revealing patterns and principles that inspire awe and humility. As quantum mechanics continues to evolve and as new generations of scientists push deeper into the quantum realm, they will undoubtedly discover phenomena that are even stranger and more beautiful than what we know today. The story of quantum mechanics is far from over, and its deepest mysteries remain unsolved. But even now, more than a century after Max Planck first introduced the quantum hypothesis, we can appreciate the extraordinary beauty and profundity of what has been discovered. Quantum mechanics reveals a universe that is more alive, more creative, and more interconnected than classical physics ever imagined. It shows us that mystery and uncertainty are not obstacles to understanding, but essential features of a reality that exceeds any finite description. The quantum universe is not cold and mechanical, but warm with possibility, alive with information, pregnant with potential that is constantly being realized through the choices and observations of conscious beings. You're not separate from this cosmic creativity, but intimately part of it, a quantum being in a quantum cosmos, dreaming quantum dreams that might themselves be part of how the universe comes to know itself. In the gentle transition between waking and sleeping, as your conscious mind begins to relax its grip on classical certainty and opens to the fluid possibilities of dream consciousness, You participate in a process that might mirror the quantum mechanical collapse of wave functions into definite outcomes. Your transition into sleep is itself a quantum phenomenon, a movement from the classical world of everyday experience into the more mysterious realm of unconscious processing and regeneration. The neural networks in your brain will continue their quantum dance throughout the night, processing information, consolidating memories, and perhaps even solving problems through quantum computational processes that classical computers cannot replicate. Your dreams might be quantum superpositions of memory and imagination, existing in multiple states simultaneously until the moment of awakening collapses them into the linear narrative of recall. But you don't need to understand these processes to benefit from them. Just as you don't need to understand photosynthesis to benefit from the oxygen produced by plants, you don't need to understand the quantum mechanics of consciousness to experience its gifts. The quantum universe supports your existence and consciousness, whether you comprehend its workings or not. This is perhaps the most comforting aspect of quantum mechanics for those seeking rest and peace. Despite all its strangeness and mystery, despite all the paradoxes and interpretational puzzles, quantum mechanics describes a universe that works beautifully and reliably. The quantum forces that hold your body together, the quantum processes that power your cellular metabolism, the quantum correlations that might bind your conscious experiences into a unified sense of self, all operate with exquisite precision and harmony. You can rest safely in the knowledge that you're held and supported by physical laws that are both utterly reliable and beautifully mysterious. The same quantum principles that seem so abstract and counterintuitive in physics laboratories are the principles that enable your heartbeat, your breathing, and the gentle electrical activity of your sleeping brain. The quantum vacuum that surrounds you, far from being empty nothingness, teems with virtual particles and field fluctuations that contribute to the stability of atoms and the structure of space-time itself. Even in the deepest vacuum of interstellar space, quantum fields continue their eternal dance, maintaining the coherence of physical law across cosmic scales. This quantum substrate of reality provides a kind of cosmic lullaby, a background hum of activity that supports all existence while remaining mostly invisible to our everyday awareness. Like the sound of distant ocean waves or the gentle whisper of wind through trees, the quantum fluctuations of the vacuum provide a soothing backdrop for consciousness, a reminder that we are embedded in processes far larger and older than our individual lives. The photons that will greet you tomorrow morning when you wake, carrying energy from nuclear fusion reactions in the sun's core, will have travelled through space as quantum fields, maintaining their coherence across millions of miles and arriving at your eyes as discrete packets of electromagnetic energy. The quantum mechanical processes that enable your retina to detect these photons and convert them into neural signals will continue the ancient conversation between consciousness and light that began when the first primitive organisms developed photosensitive cells billions of years ago. But for now, in the gathering darkness of evening, other quantum processes take precedence. The quantum tunneling reactions in your mitochondria will continue to produce the energy molecules that fuel your cellular repair and regeneration. The quantum mechanical binding forces that hold your DNA together will preserve the information patterns that define your biological identity, while allowing for the small quantum fluctuations that drive evolution and genetic diversity. Your immune system will continue its quantum mechanical patrol through your bloodstream, using quantum recognition processes to distinguish self from non-self and maintain the integrity of your biological boundaries. The quantum entanglement between electrons in neighbouring molecules will facilitate the chemical reactions that detoxify your cells and repair the accumulated damage from daily living. Even your body temperature regulation involves quantum mechanics, as the thermal motion of molecules follows quantum statistical laws that determine how heat flows through your tissues and how your body maintains the narrow temperature range required for optimal cellular function. The quantum mechanical properties of water molecules in your cells affect everything from protein folding to membrane permeability to the transmission of nerve impulses. All of these processes continue automatically, without any conscious direction from you, following the quantum mechanical laws that have governed biological systems since life first emerged on Earth billions of years ago. You can trust in this ancient quantum wisdom of your body, knowing that countless generations of evolutionary refinement have optimized these processes for your health and well-being. The transition into sleep involves its own quantum mechanical processes as neurotransmitter molecules undergo quantum conformational changes that affect their binding to receptor proteins, as ion channels in nerve membranes open and close according to quantum mechanical probability distributions, and as the electrical activity of your brain shifts into the slow, synchronized rhythms that characterize deep sleep. These sleep rhythms might themselves be quantum mechanical phenomena emerging from the coherent behavior of billions of neurons acting as coupled quantum oscillators. Some researchers speculate that the brain's ability to maintain coherence across large neural networks, despite thermal noise and environmental disturbances, suggests quantum mechanical effects at work in conscious information processing. But whether or not consciousness is quantum mechanical, sleep certainly involves quantum processes at every level, from the molecular mechanisms that regulate circadian rhythms to the cellular processes that consolidate memories and clear metabolic waste from brain tissue. Your sleep is supported by the same quantum mechanical principles that support all of life, connecting you to the deepest levels of physical reality. As you settle into this quantum embrace, consider that you are participating in processes that extend far beyond your individual existence. The quantum fields that permeate your body extend throughout the universe, connecting you to distant stars and galaxies through correlations that transcend space and time. The quantum vacuum fluctuations that provide the zero-point energy for your cellular processes also drive the expansion of the universe and the formation of cosmic structures. In a very real sense, your sleep tonight is part of the cosmic dance of quantum fields and particles that has been unfolding since the Big Bang. The same quantum mechanical principles that determine the structure of the early universe also determine the structure of your dreams. The same uncertainty principle that prevents electrons from falling into atomic nuclei also ensures that your future remains open and full of possibility. The quantum entanglement that connects particles across laboratory benches might also connect the quantum processes in your brain to quantum processes throughout the cosmos, creating a web of correlation and influence that extends far beyond our current scientific understanding. You're not isolated in your sleep, but connected through invisible quantum threads to the entire fabric of reality. This interconnectedness doesn't diminish your individuality, but reveals its true context within the larger tapestry of existence. Your unique pattern of consciousness, your personal history and relationships, your individual dreams and aspirations, all emerge from and contribute to the ongoing evolution of cosmic information processing that we call the universe. The quantum mechanical understanding of reality as fundamentally informational suggests that your thoughts, experiences and dreams are not mere epiphenomena of brain activity but genuine additions to the information content of the cosmos. Each conscious moment creates genuinely new information that becomes part of the permanent record of cosmic evolution. Your sleep tonight will generate new neural connections, consolidate new memories, and perhaps even solve problems through unconscious quantum computational processes that exceed the capabilities of any classical computer. This information processing is not separate from the quantum mechanical evolution of the universe, but an integral part of it, a way the cosmos continues to grow in complexity and self-awareness. The dreams you experience tonight will be unique creative syntheses that have never existed before and will never exist again, novel combinations of memory, imagination, and quantum uncertainty that contribute their own small but irreplaceable thread to the vast tapestry of cosmic experience. Even if you don't remember your dreams upon waking, they will have served their function in the ongoing quantum mechanical dance of consciousness and matter. But you don't need to carry the weight of cosmic responsibility into your sleep. The quantum universe is capable of managing its own complexity and evolution without conscious oversight. Your job is simply to rest and allow the deeper quantum processes to do their work of restoration and renewal. The same quantum mechanical principles that seem so paradoxical and counterintuitive when studied in physics laboratories operate with perfect reliability in your sleeping body. Quantum tunneling proceeds smoothly in your cellular metabolism. Quantum entanglement maintains the coherence of your biological systems. Quantum field fluctuations provide the background energy that supports all molecular activity. You can trust in these processes completely, knowing that they have sustained life on Earth for billions of years and will continue to sustain your life through this night and many nights to come. The quantum universe is not chaotic or unreliable, but beautifully ordered according to mathematical principles that ensure both stability and creativity, both predictability and genuine novelty. As your consciousness gradually releases its hold on the classical world of definite objects and clear boundaries, it opens to the more fluid quantum realm where possibilities coexist and identity becomes more flexible and permeable. This transition is natural and healing, allowing your neural networks to reorganize and your cellular systems to repair and regenerate. The quantum mechanical processes that will carry you through the night operate beyond the reach of worry or conscious control. They are governed by the same physical laws that govern the formation of galaxies and the evolution of stars, connecting your personal rest to the deepest rhythms of cosmic change and renewal. So rest now in the knowledge that you're supported by forces far greater and more reliable than anything you could consciously manage. Let the quantum fields that surround and permeate your being carry you gently into the restorative mystery of sleep, where consciousness and matter continue their eternal dance in forms too subtle and beautiful for waking awareness to comprehend. The quantum universe will continue its work of creation and discovery while you rest, processing information, exploring possibilities, and weaving new patterns of connection and correlation that will greet you when you wake. Your sleep is not a pause in cosmic evolution, but an integral part of it, a way the universe rests and renews itself through the consciousness of its living beings. Tomorrow you will wake refreshed and renewed, your cells repaired by quantum mechanical processes, your memories consolidated by quantum computational algorithms, your creative potential enhanced by the quantum superpositions that characterize dream consciousness. But for now, simply rest in the warm embrace of the quantum universe that is your true and eternal home. The story of how humanity discovered quantum mechanics is itself a fascinating journey through the landscape of human curiosity and scientific determination. It began in the late 1800s when physicists thought they had nearly figured out all the fundamental laws of nature. Classical mechanics could predict the motion of planets with extraordinary precision. Electromagnetic theory explained light and radio waves, and thermodynamics governed the behavior of heat and energy. But there were a few small puzzles that didn't quite fit the classical picture. When physicists heated materials until they glowed and tried to measure the spectrum of light they emitted, the experimental results disagreed with theoretical predictions in ways that seemed minor but persistent. Similarly, when they shined light on metal surfaces and measured the electrons that were knocked loose, the results followed patterns that classical physics couldn't explain. These weren't dramatic failures of classical theory, just small discrepancies that most physicists expected would eventually be resolved through better experiments or minor theoretical adjustments. No one anticipated that these tiny puzzles would lead to a complete revolution in our understanding of reality itself. Max Planck was studying the black-body radiation problem, trying to understand why hot objects emit light in the particular colors and intensities they do. Classical physics predicted that hot objects should emit infinite amounts of high-energy radiation, a prediction so absurd it was called the ultraviolet catastrophe. To make his calculations match experimental observations, Planck reluctantly proposed that energy could only be emitted and absorbed in discrete chunks, which he called quanta. Planck himself didn't believe this quantum hypothesis represented a fundamental truth about nature. He thought it was a mathematical trick that would eventually be replaced by a proper classical explanation. But Albert Einstein took Planck's idea seriously and used it to explain the photoelectric effect, showing that light itself comes in discrete particles called photons. This work earned Einstein the Nobel Prize and established the particle nature of light as a fundamental feature of electromagnetic radiation. Meanwhile, Niels Bohr applied quantum ideas to atomic structure, proposing that electrons orbit atomic nuclei only at specific allowed energy levels. Electrons could jump between these levels by emitting or absorbing photons, but they couldn't exist at intermediate energies. This quantization of atomic energy levels explained why atoms emit and absorb light only at specific wavelengths, creating the characteristic spectral lines that astronomers use to identify elements in distant stars. But the real quantum revolution began in the 1920s when physicists started developing mathematical frameworks that could describe quantum phenomena systematically, rather than just explaining isolated experimental results. Werner Heisenberg developed matrix mechanics, a mathematical formalism based on arrays of numbers that captured the probabilistic nature of quantum measurements. Erwin Schrödinger developed wave mechanics, describing particles as waves that evolve according to a differential equation now known as the Schrödinger equation. These two approaches seemed completely different at first, leading to confusion about which one correctly described quantum reality. But Max Born and others showed that matrix mechanics and wave mechanics were mathematically equivalent, just different ways of expressing the same underlying quantum mechanical principles. This unification revealed that quantum mechanics was not just a collection of isolated ideas, but a coherent theoretical framework with profound implications for our understanding of nature. The development of quantum mechanics required physicists to abandon many of their most cherished assumptions about reality. The idea that particles have definite positions and velocities, that cause and effect follow simple temporal sequences, that objects exist independently of observation, all had to be discarded or fundamentally revised. This wasn't easy for the scientists involved, many of whom struggled with the philosophical implications of their own discoveries. Einstein, despite his crucial early contributions to quantum theory, never accepted the idea that quantum mechanics represented a complete description of reality. He famously declared that God does not play dice with the universe, expressing his belief that the apparent randomness of quantum mechanics must reflect our ignorance of deeper deterministic laws. Einstein spent the last decades of his life searching for a unified field theory that would restore determinism and objective reality to physics. Schrödinger also had deep reservations about the interpretation of quantum mechanics, despite developing one of its most important mathematical tools. His cat thought experiment was intended to show the absurdity of applying quantum superposition to macroscopic objects, not to illustrate the profundity of quantum mechanics. Like Einstein, Schrödinger hoped that future developments would reveal quantum mechanics to be an incomplete or approximate theory. But experimental tests consistently confirm the predictions of quantum mechanics, even when those predictions seem to violate common sense or philosophical intuitions about the nature of reality. The double-slit experiment showed that individual particles could interfere with themselves, behaving like waves when no one was watching but like particles when their paths were observed. Bell's theorem proved that no local hidden variable theory could reproduce all the predictions of quantum mechanics, confirming that quantum correlations really are fundamentally different from classical correlations. These experimental confirmations didn't resolve the interpretational debates about quantum mechanics, but they established beyond doubt that quantum mechanical predictions are correct, regardless of what they might mean for our understanding of reality. Modern physics has learned to use quantum mechanics as a practical tool for calculating experimental results, while remaining agnostic about its deeper philosophical implications. This pragmatic approach has been enormously successful, leading to technologies and discoveries that have transformed human civilization. But the interpretational questions remain as puzzling today as they were in the early days of quantum mechanics. The measurement problem, the role of consciousness, the reality of parallel universes, all continue to generate debate among physicists and philosophers. Some find this ongoing mystery frustrating, preferring scientific theories that provide clear, unambiguous pictures of reality. But others find the interpretational puzzles of quantum mechanics to be among its most beautiful and inspiring features. They suggest that the universe might be too rich and creative to be captured completely by any finite theoretical framework, that mystery and uncertainty might be essential features of a reality that transcends human understanding. The history of quantum mechanics also illustrates how scientific revolutions typically unfold through the work of many different people, approaching the same problems from different angles. No single person discovered quantum mechanics, and no single experiment proved its validity. Instead, quantum theory emerged through the collective efforts of dozens of brilliant physicists working over several decades, each contributing pieces to a puzzle whose final shape no one could anticipate. This collaborative aspect of scientific discovery reflects the quantum mechanical principle of complementarity in an interesting way. Just as quantum systems can't be completely described from any single experimental perspective, the development of scientific theories often requires multiple approaches and viewpoints to reveal the full structure of natural phenomena. The wave-particle duality of matter and energy mirrors the theoretical experimental duality of scientific understanding. The mathematical foundations of quantum mechanics also reveal deep connections between physics and pure mathematics that weren't apparent in classical theories. Quantum mechanics uses complex numbers, infinite dimensional vector spaces, and abstract algebraic structures that were originally developed by mathematicians with no thought of physical applications. The fact that these mathematical tools turn out to be essential for describing natural phenomena suggests profound relationships between mathematical truth and physical reality. Group theory, originally developed to study the symmetries of mathematical equations, becomes essential for understanding particle physics and the fundamental forces of nature. Differential geometry, created to study curved spaces and surfaces, proves crucial for Einstein's general relativity and modern theories of quantum gravity. Topology, the study of properties that remain unchanged under continuous deformation, plays important roles in condensed matter physics and quantum field theory. These connections between mathematics and physics suggest that the universe might be fundamentally mathematical in nature, that the patterns and relationships studied by pure mathematicians reflect deep truths about the structure of reality. Eugene Wigner wrote about the unreasonable effectiveness of mathematics in the natural sciences, noting how mathematical concepts developed for their intrinsic beauty and logical consistency often turn out to describe physical phenomena with extraordinary precision. Quantum mechanics exemplifies this unreasonable effectiveness in particularly striking ways. The mathematical formalism of quantum theory, with its complex probability amplitudes and abstract state spaces, provides numerical predictions that agree with experimental measurements to more decimal places than any other theory in the history of science, yet the mathematical objects used in these calculations seem far removed from our everyday experience of the physical world. This raises profound questions about the relationship between mathematical description and physical reality. Are the wave functions and operators of quantum mechanics mere computational tools, or do they represent objective features of the natural world? Does the mathematical structure of quantum theory reflect the actual architecture of reality, or is it simply a convenient way of organizing our observations and predictions? Different interpretations of quantum mechanics offer different answers to these questions, but all must grapple with the remarkable fact that abstract mathematical relationships provide such precise descriptions of concrete physical phenomena. The success of quantum mechanics as a predictive theory is undeniable, but its ontological implications remain deeply mysterious. The development of quantum field theory in the mid-20th century deepened these mysteries, while extending quantum mechanics to describe the creation and destruction of particles. In quantum field theory, what we call particles are actually excitations in underlying fields that permeate all of space and time. The electron field, the photon field, the quark fields, and other quantum fields interact according to mathematical rules that determine the behavior of matter and energy at the most fundamental levels. This field-theoretic picture of reality is even more abstract than the original formulation of quantum mechanics, describing a universe filled with invisible fields whose fluctuations create the appearance of discrete particles and forces. Yet quantum field theory makes predictions of extraordinary accuracy, calculating properties like the magnetic moment of the electron to agreement with experiment at the level of 1 part in a trillion. The success of quantum field theory led to the development of the standard model of particle physics, which describes 3 of the 4 fundamental forces of nature and all known elementary particles in terms of quantum field interactions. The standard model has been tested in thousands of experiments over several decades, and its predictions have been confirmed with remarkable precision. The recent discovery of the Higgs boson at the Large Hadron Collider represents one of the final confirmations of standard model predictions. Yet even as the standard model succeeds as a descriptive and predictive framework, it leaves many deep questions unanswered. Why are there exactly 3 generations of quarks and leptons? Why do the fundamental constants have the particular values they do? What determines the masses and interaction strengths of elementary particles? The standard model describes how particles behave, but provides little insight into why they behave that way. Beyond these questions about the specific structure of the Standard Model, there are even deeper mysteries about the nature of quantum field theory itself. The mathematical techniques used in quantum field theory involve manipulating infinite quantities and extracting finite answers through procedures called renormalization. These techniques work extraordinarily well in practice, but their conceptual foundations remain somewhat mysterious even to experts in the field. The relationship between quantum field theory and gravity presents another set of fundamental challenges. Einstein's general theory of relativity describes gravity in terms of the curvature of space-time, while quantum field theory describes matter and energy in terms of fields defined on a fixed space-time background. Attempts to combine these approaches into a quantum theory of gravity have led to deep technical and conceptual difficulties that remain unresolved after decades of intensive research. String theory, loop quantum gravity, causal dynamical triangulation, and other approaches to quantum gravity. Each offer different visions of how space-time and matter might emerge from more fundamental quantum mechanical processes, but none of these approaches has yet produced testable predictions that could distinguish between competing theories or provide definitive evidence for any particular approach. This situation illustrates both the power and the limitations of quantum mechanics as a framework for understanding nature. On one hand, quantum principles have proven extraordinarily successful when applied to atomic, molecular, and subatomic phenomena. On the other hand, extending quantum mechanics to cosmological scales and gravitational phenomena presents conceptual challenges that push the boundaries of current theoretical understanding. The cosmological implications of quantum mechanics raise particularly fascinating questions about the nature of the universe as a whole. If quantum mechanics applies universally, then the entire cosmos should be described by a single quantum mechanical wave function that evolves according to the Schrödinger equation. But what does it mean for the universe to exist in superposition? Who or what serves as the observer that collapses the universal wave function into definite outcomes? Some cosmologists take these questions seriously, proposing models of quantum cosmology where the universe branches into multiple parallel realities, or where conscious observers play fundamental roles in the evolution of cosmic structure. Others argue that quantum mechanics breaks down at cosmological scales and must be replaced by new principles that we haven't yet discovered. The inflationary model of cosmic evolution, which explains the large-scale structure and uniformity of the observable universe, relies heavily on quantum mechanical principles. According to inflationary cosmology, quantum fluctuations in the early universe were stretched to cosmic scales by exponential expansion, creating the density variations that eventually grew into galaxies and clusters of galaxies. The cosmic microwave background radiation, the afterglow of the Big Bang, preserves a record of these primordial quantum fluctuations. This means that the largest structures in the universe, spanning hundreds of millions of light years, originated from quantum mechanical uncertainty at subatomic scales. The galaxies we observe through telescopes are fossils of ancient quantum fluctuations, cosmic scale manifestations of the same uncertainty principle that governs the behavior of individual atoms. The anthropic principle, which notes that the fundamental constants of nature seem fine-tuned for the existence of stars, planets, and life, might also be connected to quantum mechanics. Some interpretations suggest that quantum mechanics generates multiple universes with different physical laws and constants, and we observe the particular combination that allows our existence simply because we couldn't exist in universes with different parameters. This multiverse interpretation of quantum mechanics extends the many worlds idea to cosmological scales, suggesting that every quantum measurement creates new branches of reality, and that the totality of existence includes all possible outcomes of all possible quantum processes. In this view, our observable universe is just one branch of an infinitely branching tree of parallel realities. These cosmological speculations remain highly theoretical and may never be directly testable, but they illustrate how quantum mechanics continues to challenge our understanding of existence at the largest possible scales. Just as quantum mechanics revealed unexpected complexity and mystery at atomic scales, it might be revealing similar complexity and mystery in the structure of the cosmos itself. The intersection of quantum mechanics with biology represents another fascinating frontier where quantum principles might play important roles in living systems. For decades, biologists assumed that the warm, wet, and noisy environment inside living cells would destroy any quantum effects through rapid decoherence. But recent discoveries suggest that evolution has found ways to harness quantum phenomena for biological advantage. Photosynthesis, the process that converts sunlight into chemical energy in plants and bacteria, appears to use quantum coherence to achieve nearly perfect efficiency in energy transfer. When a photon is absorbed by a chlorophyll molecule, the resulting electronic excitation must find its way to a reaction center, where it can be converted into chemical energy. Classical physics would predict that this process should be relatively inefficient, with much of the energy lost to heat and other wasteful pathways. But experimental studies using ultra-fast laser spectroscopy have revealed that photosynthetic systems maintain quantum coherence for much longer than expected, allowing the electronic excitation to explore multiple pathways simultaneously and find the most efficient route to the reaction center. This quantum mechanical process might explain why photosynthesis achieves energy transfer efficiencies approaching 100%. Similar quantum effects might be important in other biological processes. Some birds navigate using the Earth's magnetic field, and recent research suggests this ability depends on quantum entanglement in specialized proteins in their eyes. The quantum states of electrons in these proteins are sensitive to magnetic fields, providing a kind of quantum compass that helps migratory birds find their way across vast distances. The sense of smell might also involve quantum mechanics. The vibrational theory of olfaction proposes that we detect odor molecules by sensing their quantum mechanical vibrational frequencies rather than just their molecular shapes. This would explain why molecules with similar shapes can have very different smells, and why molecules with different shapes but similar vibrational frequencies can smell alike. Even more speculatively, consciousness itself might emerge from quantum processes in the brain. The integrated information theory of consciousness proposes that conscious experience corresponds to integrated information processing that transcends the classical boundaries between different brain regions. Quantum entanglement might provide a mechanism for this kind of non-local information integration. Penrose and Hameroff's orchestrated objective reduction theory suggests that consciousness arises from quantum processes in microtubules, protein structures that help maintain the shape and organization of brain cells. According to this theory, quantum superpositions in microtubules persist until they reach a critical threshold and collapse into definite outcomes, creating moments of conscious experience. These theories remain highly controversial and largely unproven, but they illustrate how quantum mechanics might be relevant to some of the deepest questions about life and consciousness. If quantum effects really are important in biological systems, then understanding life might require understanding quantum mechanics at levels of complexity and organization that we're only beginning to explore. The technological applications of quantum mechanics continue to expand as our ability to manipulate quantum systems improves. Quantum computers represent perhaps the most dramatic example, promising to solve certain problems exponentially faster than any conceivable classical computer. But quantum technologies extend far beyond computing into sensing, communication, and simulation. Quantum sensors can detect gravitational waves from colliding black holes, measure magnetic fields with extraordinary sensitivity, and track the motion of individual atoms with unprecedented precision. These capabilities arise from the quantum mechanical property of entanglement, which allows multiple particles to be correlated in ways that amplify weak signals and reduce measurement noise. Quantum communication systems use entanglement to provide security that is guaranteed by the laws of physics rather than by computational complexity. Any attempt to intercept a quantum communication necessarily disturbs the quantum states being used to encode information, immediately alerting the legitimate parties to the presence of an eavesdropper. Quantum simulation might provide insights into complex many-body systems that are impossible to study using classical computers. High-temperature superconductors, exotic magnetic materials, and strongly correlated electron systems all involve quantum mechanical effects that are too complex for classical computational methods. Quantum simulators built from carefully controlled quantum systems might reveal the principles underlying these phenomena and guide the development of new materials with revolutionary properties. The transition from laboratory demonstrations to practical quantum technologies requires overcoming significant technical challenges related to quantum error correction, system scalability, and environmental isolation. Quantum states are extremely fragile and can be destroyed by even tiny interactions with the surrounding environment. Building large-scale quantum systems requires developing methods to protect quantum information while still allowing controlled operations. Recent progress in quantum error correction has shown that it's theoretically possible to build quantum computers that remain stable even when individual components are imperfect and noisy. This requires using many physical qubits to encode each logical qubit of information, with redundancy and error correction protocols that can detect and correct errors faster than they accumulate. The race to build practical quantum computers has attracted enormous investment from governments and technology companies around the world. Google, IBM, Microsoft, and other major corporations have built increasingly sophisticated quantum processors, while startups and research institutions explore alternative approaches using different physical systems like trapped ions, superconducting circuits, and photonic networks. But even as quantum technologies advance, the fundamental interpretational questions about quantum mechanics remain as mysterious as ever. Building practical quantum devices requires understanding how to manipulate quantum systems, but it doesn't require resolving debates about the nature of quantum reality or the role of consciousness in quantum measurement. This separation between practical quantum technology and fundamental quantum interpretation reflects a broader pattern in the history of science and technology. We learned to use electricity long before understanding electromagnetic theory, to fly airplanes before fully understanding fluid dynamics, to build computers before developing comprehensive theories of computation. Practical applications often precede complete theoretical understanding. But the interpretational mysteries of quantum mechanics seem deeper and more persistent than the conceptual puzzles that accompanied previous technological revolutions. After more than a century of experimental confirmation and technological application, we still don't have consensus about what quantum mechanics tells us about the nature of reality. This ongoing mystery might reflect fundamental limitations in human understanding, rather than temporary gaps in scientific knowledge. The quantum world operates according to principles that seem to transcend the categories of classical logic and everyday experience. Perhaps consciousness evolved to navigate a classical world of medium-sized objects moving at moderate speeds, and simply lacks the conceptual resources to fully comprehend quantum reality. Alternatively, the interpretational puzzles of quantum mechanics might be pointing toward new levels of understanding that we haven't yet achieved. The history of science shows repeated instances where apparent paradoxes and conceptual difficulties eventually led to deeper insights and revolutionary new perspectives. The wave-particle duality that seemed so paradoxical in the early days of quantum mechanics is now understood as a natural consequence of the mathematical structure of quantum theory. Similarly, the measurement problem and other interpretational puzzles might eventually be resolved through new theoretical developments that we can't currently imagine. The unification of quantum mechanics with general relativity might reveal new principles that clarify the relationship between quantum and classical reality. The development of quantum theories of consciousness might explain the role of observation in quantum measurement. But it's also possible that the interpretational mysteries of quantum mechanics reflect fundamental features of reality that will never be completely resolved. Perhaps uncertainty, complementarity, and observer dependence are irreducible aspects of existence that must be accepted rather than explained away. Perhaps the quest for complete understanding is itself based on classical assumptions that don't apply to quantum reality. These questions reach beyond physics into philosophy, religion, and human meaning. If quantum mechanics tells us that reality is fundamentally uncertain and observer-dependent, what does this mean for our understanding of truth, knowledge, and existence? How should we live in a quantum universe where the future is genuinely open and where consciousness might play a fundamental role in the unfolding of reality? Different people will answer these questions differently, depending on their philosophical perspectives, religious beliefs, and personal experiences. But quantum mechanics provides a scientific foundation for approaches to life that emphasize uncertainty and interconnectedness, and the crave role of consciousness in shaping reality. The quantum worldview might encourage humility in the face of mystery, acceptance of uncertainty as a fundamental feature of existence, and recognition of the deep connections that link all aspects of reality. It might support attitudes of openness, creativity, and wonder, rather than rigid dogmatism or mechanical reductionism. But these philosophical and spiritual implications of quantum mechanics must be approached with care and critical thinking. The history of science includes many examples of premature attempts to derive broad worldview conclusions from specific scientific theories. Quantum mechanics describes the behavior of atoms and subatomic particles under carefully controlled laboratory conditions. Extending these insights to human affairs requires additional evidence and argumentation that goes beyond physics itself. Nevertheless, quantum mechanics does provide a powerful counterpoint to worldviews based on classical physics and mechanical determinism. It shows that even at the level of fundamental physics, reality is more mysterious, creative, and interconnected than classical science suggested. This creates conceptual space for phenomena like consciousness, creativity, and meaning that seem difficult to explain in purely mechanistic terms. The ongoing development of quantum mechanics also illustrates important features of scientific progress itself. Science doesn't advance through the accumulation of isolated facts, but through the development of increasingly comprehensive theoretical frameworks that reveal new connections and possibilities. The quantum revolution in physics wasn't just about discovering new phenomena, but about developing new ways of thinking about phenomena we thought we already understood. This process of conceptual revolution continues today as physicists work to extend quantum mechanics to new domains and resolve its remaining conceptual puzzles. The development of quantum gravity, quantum cosmology, and quantum theories of consciousness might lead to new revolutionary insights that transform our understanding of reality as dramatically as the original quantum revolution transformed classical physics. Future generations might look back on our current understanding of quantum mechanics the way we look back on classical mechanics, as a useful but limited approximation to deeper truths about the nature of existence. The quantum weirdness that seems so strange to us might seem natural and obvious to people who grow up with quantum technologies and quantum ways of thinking. But even if future developments reveal our current understanding to be incomplete or approximate, the core insights of quantum mechanics seem likely to remain valid. The uncertainty principle, wave-particle duality, and quantum entanglement appear to be fundamental features of reality that any future theory will need to incorporate rather than eliminate. The mathematical structure of quantum mechanics, with its complex probability amplitudes and non-commuting operators, captures deep truths about the nature of information, measurement, and correlation that transcend any particular physical interpretation. These mathematical relationships might persist even if our understanding of their physical significance continues to evolve. As we contemplate these vast questions about the nature of quantum reality, it's worth remembering that you don't need to resolve the interpretational puzzles of quantum mechanics to benefit from living in a quantum universe. The quantum processes that sustain your life, enable your consciousness, and connect you to the cosmos operate reliably and beautifully, regardless of how completely we understand their deeper significance. Your body is a quantum mechanical system of extraordinary complexity and sophistication, maintained in a state of dynamic equilibrium through countless quantum processes that have been refined by billions of years of evolution. The quantum tunneling in your cellular metabolism, the quantum coherence in your neural networks, the quantum correlations that might bind your conscious experiences together, all operate with exquisite precision to support your existence and well-being. The atoms that compose your body were forged in the quantum furnaces of ancient stars, dispersed through space by stellar explosions, and assembled into the complex molecules of life through quantum mechanical processes that continue to operate in every cell. You're literally made of stardust. Quantum stardust that carries the memory of cosmic evolution in its very structure. The photons that illuminate your world were created through quantum mechanical processes in the sun's core, traveled through the vacuum of space as quantum fields, and were absorbed by quantum processes in your eyes. The solid objects around you are held together by quantum forces. The electronic devices you use operate through quantum effects, and the chemical reactions that enable life depend on quantum mechanical principles. Even your thoughts and dreams might be quantum phenomena emerging from quantum computational processes in your brain that tap into the same fundamental principles that govern the behavior of atoms and the evolution of stars. The boundary between your inner world of consciousness and the outer world of quantum fields and particles might be less clear than everyday experience suggests. But you don't need to understand these connections intellectually to participate in them experientially. Just as you don't need to understand the biochemistry of digestion to enjoy a meal, you don't need to understand the quantum mechanics of consciousness to experience the wonder and beauty of conscious existence. The quantum universe supports and sustains you whether or not you comprehend its workings. The quantum fields that permeate space provide the foundation for all matter and energy. The quantum processes that drive stellar fusion create the heavy elements essential for life. The quantum forces that bind atomic nuclei together maintain the stability of matter across cosmic timescales. You can rest peacefully in the knowledge that these quantum processes operate with reliability and precision that far exceeds anything achievable through human design or intention. The same physical laws that seem so mysterious and counterintuitive in physics laboratories provide the stable foundation for your existence and the existence of everything you encounter. The quantum mechanical universe is not chaotic or arbitrary, but beautifully ordered according to mathematical principles that ensure both predictability and creativity, both stability and genuine novelty. The apparent randomness of quantum measurements reflects genuine indeterminacy that provides a source of creativity and surprise, while the deterministic evolution of quantum wave functions ensures that this creativity unfolds according to comprehensible patterns. This combination of order and openness, predictability and surprise might be essential for the existence of consciousness and life. A perfectly deterministic universe would leave no room for creativity or choice, while a completely random universe would lack the stability needed for complex structures to persist. The quantum universe provides just the right balance of order and chaos to support the emergence of complexity, consciousness, and meaning. As you prepare for sleep, you can trust in this quantum foundation that supports all existence while remaining largely invisible to everyday awareness. The quantum vacuum that surrounds you teems with virtual particles and field fluctuations that contribute to the stability of atoms and the structure of space-time. The quantum correlations that connect distant particles might also connect you to the far reaches of the cosmos in ways that transcend classical notions of space and time. Your sleep will be supported by quantum processes that operate at every level of biological organization, from the molecular machines that repair cellular damage to the neural networks that consolidate memories and clear metabolic waste from brain tissue. The quantum mechanical properties of the molecules in your body determine everything from the efficiency of energy production to the fidelity of genetic replication to the speed of neural transmission. These processes have been optimized by evolution over billions of years to function reliably in the quantum environment of biological systems. You can trust completely in their wisdom and effectiveness, knowing that they will continue their work of maintenance and renewal while your conscious mind rests. The transition into sleep itself involves quantum mechanical changes in the electrical and chemical activity of your brain, as ion channels open and close according to quantum probability. Distributions and neurotransmitter molecules undergo quantum conformational changes that affect their binding to receptor proteins. The slow, synchronized rhythms of sleep emerge from the quantum mechanical interactions of billions of neurons acting as coupled oscillators. But you don't need to understand these mechanisms to experience their benefits. Your nervous system knows how to make the transition into sleep through quantum processes that operate below the threshold of conscious awareness. Your job is simply to relax and allow these deeper processes to do their work. As your consciousness gradually releases its grip on the classical world of definite outcomes and clear boundaries, it opens to the more fluid quantum realm where possibilities coexist and identity becomes more flexible and permeable. This transition is natural and healing, allowing your neural networks to reorganize and your cellular systems to repair and regenerate. The dreams you experience during sleep might represent a kind of quantum consciousness, where the normal constraints of classical logic and linear causality are relaxed, and your mind can explore superpositions of memory, imagination, and possibility. Dream consciousness might operate according to quantum rather than classical principles, allowing for the kind of creative synthesis and non-local correlation that characterizes quantum systems. But whether or not dreams are literally quantum mechanical, they certainly serve quantum-like functions in the organization and processing of information. Dreams allow your brain to explore counterfactual scenarios, to make unexpected connections between disparate experiences, and to reorganize memories in ways that support learning and creative problem-solving. The information processing that occurs during sleep might tap into quantum computational resources that exceed the capabilities of classical neural networks. Some researchers speculate that the brain operates as a quantum computer during certain phases of sleep, using quantum superposition and entanglement to perform calculations that would be impossible for purely classical systems. These ideas remain speculative, but they illustrate how quantum mechanics might be relevant to the most intimate aspects of your personal experience. Your consciousness, your dreams, your memories, your creative insights might all emerge from quantum processes that connect you to the deepest levels of physical reality. As you drift towards sleep, you participate in quantum processes that extend far beyond your individual existence. The quantum fields that support your biological functions extend throughout the universe, connecting you through invisible correlations to distant stars and galaxies. The quantum vacuum fluctuations that provide zero-point energy for your cellular metabolism also drive the expansion of the universe and the formation of cosmic structure. Your sleep tonight is part of the cosmic evolution of information and complexity that has been unfolding since the Big Bang. The quantum mechanical principles that govern your neural activity also govern the quantum fluctuations in the early universe that eventually grew into galaxies and solar systems. The same uncertainty principle that makes your future genuinely open also ensured that the primordial cosmos was filled with the quantum seeds that eventually became stars, planets, and life. In a very real sense, your individual existence represents a temporary localization of cosmic information processing, a way the universe has developed of knowing and experiencing itself through conscious beings. Your thoughts and experiences tonight will add new information to the cosmic record, contributing novel patterns of meaning and beauty to the ongoing evolution of reality. But this cosmic perspective doesn't diminish the importance of your personal rest and renewal. The universe evolves through the experiences of individual conscious beings, and your well-being contributes to the overall health and creativity of the cosmic process. Taking care of yourself is a way of taking care of the universe itself. So rest now in the knowledge that your sleep serves cosmic as well as personal purposes, that the quantum processes carrying you into dreams are part of the same fundamental creativity that drives the evolution of stars and the emergence of consciousness throughout the cosmos. Let yourself be gently carried by quantum currents that are older than the Earth and more reliable than any human institution. The mathematics that describes these quantum processes represents some of the most beautiful and profound insights in the history of human thought. The Schrödinger equation, which governs the evolution of quantum wave functions, captures the essence of how possibility becomes actuality through the mysterious process of measurement. The commutation relations between quantum operators encode the fundamental uncertainty that prevents reality from being completely predictable or controllable. But you don't need to understand the mathematics to be supported by the physical processes they describe. The quantum mechanics of your sleeping brain operates according to these same elegant equations, processing information and maintaining coherence through mechanisms that exceed our current theoretical understanding but demonstrate their effectiveness through billions of years of evolutionary refinement. As your consciousness settles into the quantum embrace of sleep, it joins the vast community of sleeping minds across the planet, each supported by the same quantum mechanical processes, each contributing to the global pattern of neural activity that might constitute a kind of planetary nervous system. The electromagnetic fields generated by sleeping brains around the world create subtle resonances that connect individual consciousness to collective patterns of information processing. These connections remain largely hypothetical, and certainly don't override individual autonomy or privacy, but they suggest that consciousness might be more interconnected and less isolated than our everyday experience suggests. The quantum entanglement that connects particles across vast distances might also connect minds across social and geographical boundaries in ways that we're only beginning to explore. Your dreams tonight will be uniquely yours, emerging from your personal history and individual neural patterns, but they will also participate in broader patterns of meaning and creativity that transcend individual boundaries. The archetypes and symbols that appear in dreams might represent collective information processing that operates at quantum scales of correlation and influence. But these speculative connections to collective consciousness and cosmic evolution are less important than the simple fact that your sleep tonight will be supported by the most fundamental and reliable processes in the universe. The quantum mechanical laws that govern atomic behavior have been stable for billions of years and will continue to operate long after human civilization has evolved into forms we can't currently imagine. You can rest completely in this quantum foundation, knowing that the same principles that maintain the coherence of matter also maintain the coherence of consciousness, that the same forces that hold atoms together also support the neural networks that generate your thoughts and dreams. The universe that seems so vast and impersonal from a classical perspective reveals itself as intimately connected and personally meaningful when viewed through the lens of quantum mechanics. Tomorrow you will wake to a world where quantum processes continue their eternal dance of creation and discovery, where the solid objects of everyday experience continue to emerge from the fluid possibilities of quantum fields, where consciousness continues to participate in the ongoing evolution of cosmic information and meaning. But for now, simply rest in the warm quantum embrace that connects you to everything that was, is, and ever shall be.